Okay, so next area that I want to look at, I suppose, is another really important area for us in statistics in general. And with statistics, we're all about data. We're all about looking at the data we have, interpreting the data, presenting the data, making conclusions, inferring things from what we've been presented, basically. And part of that is going to do with us looking at how the data is distributed. And we've already kind of looked at this in some sense when we looked at standard deviation. We're looking at how spread out the data is. We have that sense that maybe we want data usually to be less spread out so that it's typically more consistent. So if I'm looking at like test results or something like that, I would usually want a lower standard deviation because that would suggest that my results across different tests are fairly consistent, that they're not hugely spread out, that I'm typically falling close to whatever my average may be. When we're looking at the shape of the data more generally, we're maybe looking at data that's often presented on, say, histograms, is one of the common forms, I suppose, or the common areas that we're looking at. And we're maybe looking at how does the data fall. Okay, so how does it kind of fall? If we look at the chart, how can we describe where most of the data is and where a bit of the data is, or what's affecting it from not being perfect, I suppose. So the ideal sort of data that we could come across would be data that is kind of roughly normal, or that falls in kind of a normal, and we look for something that's sort of symmetrical. So we would like to see most of the data in the middle and then kind of falling either side and kind of as even as possible. So ideally, the ideal sort of data would fall perfectly evenly either side. So we'd have, say, the tallest bar in the middle and the other two bars here falling or decreasing in an even way the entire way down. That would be perfectly normal data, suggesting that most people are in the middle, and as we go further down, we're falling in similar ways both above and below the mean. Now, obviously, for the data that we're looking at, that's not always going to be the case. And instead, we're going to be looking at certain types of data which could be skewed in certain directions. And the way we describe the skew is we look at which direction the data is being pulled in. So say we look here, most of the data in this one is up on this far end, but there is some of the data at the tail end to the right that is pulling it in this way. Okay, so that is skewed to the right. We would even go as far as kind of saying that that is kind of positively skewed. Okay, so we could even say that that is positively skewed. And then skewed to the left would be negatively skewed. Okay, this will have an effect on our different averages. If we think about it, the mode is the most often one, the one that's there the most frequent. So that's typically going to stay the same. In a histogram, that's fairly clear. It's the tallest bar. The median is the middle one. So that has to kind of fall somewhere in the middle. And then I suppose the mean is the last one, and the mean is often affected by outliers. So having really high values is going to affect your mean because it's going to increase your mean. In the same way as when it's skewed to the left or skewed negatively, that means we're introducing, or we have quite small values that have caused the mean to go down, that are kind of dragging it downwards, where the mode stays at the top as the most common one and the median falls still somewhere in the middle. We may be asked, or we may have to think about examples of these different types of data. So in the first example here, where it's skewed to the right, where most of my information is at the lower end, but some is at the higher end, you could look at things like the age that you learn to ride a bike, the age that people do their leaving cert. You're looking for things where most people, or most of the data you would expect to collect, would fall in the lower end, but there is potential for there to be data at the higher end as well. So the same thing if we're looking for the second example here, skewed to the left, where most of the data is at the higher end, and it doesn't have to be in the hundreds, it just has to be at a higher end. We might look at, say, the age people get married, the age people start wearing reading glasses is quite a common one. So obviously that can happen younger, but tends to really kind of grow when you get to older ages. So things like that are good examples of different types of data and kind of where they would fall. Obviously, as I said, the ideal sort of data we would get would be normally distributed data. And there we look at things like kind of IQ, heights, things like this, that if you take a large sample of people or a large proportion of people and survey them, you would expect it to fall in a roughly normal distribution here. And this normal distribution is incredibly important for us when we're working with different statistics. It allows us to make conclusions, to infer probabilities, to kind of describe the data in a much more accurate way than we could for any of the other types of data sets that we get. The key things with the normal distribution are that it is symmetrical, so it has a high point in the middle and it falls evenly either side, that 50% of the data falls either side of that middle value, so it kind of makes sense since we have a nice middle, there's obviously half of the data on either side. We would say it's symmetrical about that middle value or around that middle value. All three averages of the mean, median, and mode should line up with each other into that central value. And I suppose this is where our idea of a bell-shaped curve comes from to some sense. So people talk about the bell curve, and this is really what they're getting at. They're looking for a normal distribution, because that gives kind of a nice view of that sense as well, that we've a lot of data in the middle and we've evenly kind of coming out either side, and we end up with nice proportions as well falling in certain sections of our data here. So one of the key rules that we use that stems from this normal distribution is called the empirical rule. And the empirical rule is incredibly important. The empirical rule tells us what proportion, and particularly really percentage, of the data we would expect to find at certain intervals along this curve. And what we use when we're looking at these percentages is we use standard deviation. And standard deviation, if we remember, is a measure, it's like an average distance that the value is from the mean. So what we do is we look at loads of all of our data points, and we see how far are all of my data points from the mean, and we do a calculation which basically kind of involves us calculating nearly like an average distance. So how far on average are my data points from the mean, and then we use that in further calculations. So with the empirical rule, we're really working with that standard deviation, and we're using that to kind of comment on how far someone's result or point of data may be from the average or from the mean, and I suppose here specifically from that middle value. So obviously, since it's in the middle, we could have data that is above the mean, but we also have data that is below the mean. And what the empirical rule tells us is it tells us that, for example, 68% of the data is within one standard deviation, and that means plus or minus, so either one above or one below. If we take that full section, we should get about 68% of our data. In the same way, if we go further, if we go 2 steps, 2 standard deviations away from the mean either side, we should get 95% of our data. If we go 3, we should have 99.7% of our data. So there's always a little bit left over at each case there. There's some of the data that's not included, but as we go further, as we allow ourselves to get further from the mean with 3 standard deviations, we're including basically all of the data under the curve. So I kind of have this laid out a bit more explicitly over here to the right hand side. So this idea that under this normal curve, if I go 1 standard deviation above and below, I will account for 68% of my data, and we can even go further because it's symmetrical. We can even go further and say that that is 34% either side. If we go a little bit further then and go for 2 standard deviations either side, we will get 95% of the data, which is even 47%, 47.5%, okay, nearly 48%. And the same with 99.7. If we go that far, we're including most of the data with the little bit left over. And that idea that it's always split in half. It can even be important as well to look at what's left. If I have 95% of my data included, that would suggest that 5% of my data is not included, and that's correct, but actually there's 2.5% on either side here. Okay, and if we added up all of that, you can see 47.5 plus 2.5, that would give me 50. And the same on the other side would give me 50 as well. So that sense, I suppose, that across all of these questions, we're really paying attention to what proportion or what percentage of the curve is included in each calculation. And that's going to be really crucial for us in working out a lot of these different values. So same with the 99.7, there's 0.3% included or left out there. So 0.15% either side. So a tiny percentage, but equal percentage either side. So the reason this empirical rule is so important is that if we are presented with data that is normally distributed, it's going to leave us better able to answer those questions, essentially. So let's look at an example. Here, the finishing times for a cross-country race were normally distributed with a mean time of 13 minutes and a standard deviation of 1.5 minutes. The diagram below shows the distribution of the finishing times. Use the empirical rule to answer these questions. So we're asked first of all to use the mean and standard deviation to fill in the missing numbers. So let's see how we would do that. Well, with a normal curve, we expect to find the mean value bang in the center. So let's see what the mean value is here. It's 13 minutes, so my 13 should be right in the center here. We then have a standard deviation of 1.5. What that standard deviation should represent is it should represent the different steps that I take to move both upwards and downwards in my data. So each time I go up a certain step, I'm going up by 1.5. Okay, that represents how I'm going to take those steps. So we can see that that lines up with what they have. They've gone from 13 to 14.5, which is a step of 1.5. If we do another step of 1.5 here, we're going to end ourselves up at 16. We can also go down by 1.5. So that's going to take us to 11.5 and take us to 10. So we're able to go up and down by 1.5. So looking at kind of where we're at now, we're basically saying that the people in this cross-country race took around about an average of 13 minutes to finish the race, but we could have had, for example, here, anywhere between 10 and 16 minutes, and we can even go further if we go further standard deviations away. So we're asked first of all to use the mean and standard deviation to fill in the horizontal axis. We've done that. We're then asked what percentage of the runners who finished the race had a finishing time between 11.5 and 14.5 minutes. So let's see where those are on our diagram. Well, 11.5 is here and 14.5 is here. If we look at how many steps we've had to take either side here, we took one step or one standard deviation upwards to get to 14.5, and we took one standard deviation downwards to get to 11.5. So we would say here that we have gone up and down one standard deviation, or we're within one standard deviation. And if we look or remind ourselves of what proportion that would be 68% of my data. So 68% of runners took between 11.5 and 14.5 minutes. They're then giving us how many runners finished the race. So that's good. Okay, so we'll use that in the next part. Find the number of runners who had a finishing time between 11.5 and 16 minutes. Okay, so let me just actually erase this side here. So 11.5 and 16, let's highlight those two. So 11.5 is here, 16 is here. So if I go down to 11.5, we've already looked at this. That is one step, that is down one standard deviation. We already know from what we set up here that one standard deviation within one standard deviation means 68%, but to get more specific, it means 34% either side because it's symmetrical. Now, if I'm only looking at one side here, that would mean that there's 34% within this one section that I've put in first of all, between 13 and 11.5. To look next at all at how we would get to 16, well, that requires me to do not just one, but two steps. Okay, two standard deviations. So let's have a look at our chart again. Two standard deviations in total is 95%, but since I'm only looking at one half, I could take half of that, which is 47.5%. Okay, 47.5%. So let's mark that in here. This is 47.5%. So taking those together now, we have, this is part 3, we have our 34% on the left hand side, our 47.5% on the right hand side. So let's add those together. That's going to be 81.5%. So quite a large proportion of the data, more than 68 but less than 95, which is what we would expect here because we've only gone more on one side of the graph. They actually asked us how many runners though, so it's 81.5% of 120 runners. So important, I suppose, for ourselves as well that we do add in that extra layer because we have to go further here and not just give the percentage but actually go further and work out how many people that's going to be also. So if we take that, so we can do that on our calculator, multiplying our answer, and let me just see what that will give me here for this one. That's going to give me So 120 by 81.5%, that's going to give me 97.8 people. So if we take only the total people, that would be 97 people. Okay, so 97 people finished within that range. We had a person, we have maybe half a person, but obviously we can't include part of a person. So we'll go with 97 full people definitely finished there. For part 4, how many runners finished in less than 10 minutes? Well, let's have a look and see where that 10 minutes is. So I'm just going to erase my previous work here again. So 10 minutes, we have a little bit to do with this one. Bits that came off there. So 10 minutes is down here. That is me taking 2 steps downwards. So we already know from working in the last one that that is 47.5% here that we've included. Let's go the other way around though. We don't want that side, we actually want this side. So in order to work that out, we need to remind ourselves that the full section is 50%, which would suggest then that this is 2.5% that is left, because the full half of the data should be 50%. So 2.5% finished with less than 10 minutes. So let's work that out, which is 3 people. So 3 people finished the race in less than 10 minutes, which in this case obviously is quite a high score. Okay, so in fact, even though it's a low value, because of the context, that's actually a really good score. That's actually quite a high score and a good achievement there. So hopefully we're getting a sense so far of the need for us to really remember those different proportions, those different percentages, but not even just remembering the total values, remembering also that we can divide that in half to only work on one side or the other side of this graph here, and even also that we can work outside of those proportions as well. So let's have a quick fly through some of the other exam questions that go here. Usual story, give a go to these yourself, and then if you're stuck on any of them, you can obviously use this for a bit of help or a bit of guidance. So this is the one 2025, so this was, I suppose, last year's one for now. So let's fill in the different values that we can. They told me the mean mark is 62, that always goes in the center. We're going to highlight the standard deviation. That's going to be the different steps that I'm going to be taking. So I'm going to be going up in 14. So I go up in 14 here. First of all, that's going to give me to 76. I go up in 14 again. That does bring me to 90. So they've actually added in a number that I can use to check. I go down by 14. That gives me to 48. I go down another 14. That gives me to 34. So we've filled in all of our information. First question says, find the probability a student had a mark between 34 and 90. Well, for each of these, that is 2 steps and 2 steps, so nice and easy. It's just one of our normal answers. 2 standard deviations is 95%. 150 students at the exam. Estimate the number of students who got marks between 48 and 76. So 48 is here, 76 is here. That's just 1 step either side, and we know that that is 68%. So 68%. But here they want how many people, so 68% of 150. We can calculate that using a calculator to get our answer. That is 102 students. So again, really just fluently using those different proportions, using those different percentages. Let's look at another example. In a survey, the IQ scores of 1,200 people were recorded. The mean score was 100, so I'll fill that in as we go. The mean score was 100. The standard deviation was 15. So we're going up in 15s here. So let's go up 115, up again, 130, up again, 145, down to 85, which is great because that does line up with what we have, down to 70, and down to 55. So we've filled in the missing numbers. A person is chosen at random. Find the probability this person has IQ scores between 70 and 130. So if we look at those two, to go up to 130, that is 2 steps. To go down to 70, that is 2 steps. So it's even on both sides, the same amount either way. That should just be one of those numbers we've learned off, which is 95% in this case. So 2 standard deviations is always 95%. We're then asked to use the empirical rule to find the number of people surveyed with IQ scores between 85 and 115. So let's highlight those ones. 85 and 115. Again, that's 1 step to the side here to get to 85, one step to get to 115. That's one of our learned ones here, which is 68%. It's 68% of 1200, so we can calculate that value, because here they want the people as opposed to just the proportion, and that is 816 people. Into another example now, 2024. So kind of we're looking at, I suppose, the few recent years. A large group of 17-year-olds were asked how many hours sleep they got. The results were normally distributed. The middle 68% slept between 7.2 and 8.4 hours, as shown on the diagram below. Let's highlight that for ourselves. We already know that 68% should represent one standard deviation. So going up one of those standard deviations, one of those steps, and going down one of those standard deviations. So going from here to here and from here to here should be 2 steps or 2 standard deviations. Let's see what that distance is. 8.4 to 7.2, well, that's 1.2. That 1.2 was 2 steps, which would mean that one step needs to be 0.6 or 1 standard deviation. So let's see, that would bring me to 7.8 here, and then up to 8.4 to 9 and to 6.6. So we can fill it out nice and easy there, but just taking that extra step just to work out exactly what's happening in this case, knowing for ourselves that that was 2 steps, and then using that to work it downwards. Looking at part 2, research says a 17-year-old should get at least 9 hours of sleep. What percentage of this sample got at least 9 hours of sleep? Well, let's see. Going up as far as 9 hours here, well, that means including, let's focus on the right hand side. So that's going up 2 steps, okay, or 2 standard deviations. We know that that's 95. If I'm only looking at this half, then half of that 95 is 47.5%, which leaves a little 2.5% up to the outside here. Leaves us with a little 2.5% to the outside. So there were 2.5% who got at least 9 hours. They got 9 or more. So 2.5% of people, okay, of 17-year-olds. We're not actually asked to work out how many. So 2.5%. One last question for us from 2011. The heights of a given population are normally distributed, very similar to the last one. This time it's 95%, which we'll make a little note for ourselves. We know that's 2 standard deviations, bringing me to 95%. So if we look at how that would work, to go from 147.9 to my middle mean value, and then onwards to 178.7, we would have to do 2 steps and 2 more steps upwards. So let's calculate the distance here. 178.7 minus 147.9. So what is our distance here? It's 30.8, and that is 4 steps. So 1 step then is 7.7. And we can kind of test it out for ourselves, going up 1 round of 7.7, going up 1 round of 7.7 does indeed, or sorry, 2 rounds of that 7.7 brings us to the mean. We don't know what the mean is, and then the 2 more, yeah, checking that that does bring us right up to the top value that we want. Let's calculate what we would need here. So going up 2 rounds of 7.7 here to bring me to my mean value is 163.3. So to answer their questions fully, the mean is 163.3 and the standard deviation is 7.7. So what we need to remember from this, well, first of all, a little bit about the shape of the distribution, the skew of the data, being able to make a description or to make a comment on that. Then more specifically looking into the normal curve, remembering that normal distribution, my mean is in the center, half of my data is on either side of the mean there, and that I have a specific rule, the empirical rule, which tells me which proportion or percentage of data can be found 1 standard deviation, 2 standard deviations, 3 standard deviations from the mean. Further to that as well, remembering that I can half those different numbers. So 68% yes, but 34% either side. 95% yes, but 47.5% either side, and 2.5% then outside of that. Remembering all three of those is really going to help us. For all of the questions we had there, we were basically given a diagram. If we weren't, I would definitely be making sure that I would draw my own diagram, because that would kind of help guide me then.